The next speaker is Giat Valley on composition of space-time.
How do I make the full screen? Slideshow. Oh, sorry. Okay, great. Well, okay, thank you very much for invitation to this great conference. And before I start, I want to say a couple of words. I was a young postdoc here in Pisa, so I consider Pisa like my alma mater with Riccardo. It was an unbelievable experience. I learned many things from Riccardo, most importantly the attitude and what physics is about. And I really want to thank for all this Riccardo very much. Thank you very much. It's a great pleasure and honor to be here for this conference. And okay, so I will try to, is there a point? Yeah, this is the point. So I will try to discuss some new ideas that we are very much excited about. This is about, one can call this set of this framework quantum compositeness of gravity or of space-time. This is mostly in collaboration with Cesar Gomez and a bunch of students of mine, Nico Winterguest, Daniel Flessing, and Alex Pretzel in particular in this talk. And so the idea is to, so the big picture is that to understand what we normally think as a classical field, quantum mechanically as a composite entity. Now, and then once you make this assumption, which to me is not even an assumption, it's the only option. Otherwise, I cannot even imagine, because in quantum physics, everything is composite of quanta. Then some interesting things open up, and this is what I want to share with you. Now, as we know, in gravity, every source, every gravitating object has a gravitational radius, associated gravitational radius, a Schwarzschild radius. The same is true about the universe, but the universe also has a second radius, which is so-called Hubble radius. Now, for the certain class of universes, these two radii are the same. So, for instance, in our universe, the Schwarzschild radius of our universe is extremely close to the Hubble radius. In fact, as long as we can tell, it's equal. So this means that there is some deep similarity between black holes and cosmological spaces. Therefore, what I will discuss, I will try to apply to both of these cases. Now, one thing which is very interesting, what emerges, is the following. Now, normally we think, so the thing about what is classicality and what is quantumness. Now, normally we think that big things are classical. For example, a black hole, any black hole which is heavier than the Planck mass, must be, is in a good approximation, should be classical. Planck mass is approximately 10 to the 5 grams, mass of amoeba. In particular, a black hole of the size of the universe, of the mass of the universe, will have size 10 to the 28 centimeters. Now, everybody in with the normal quantum mechanical intuition. Oh, sorry, -5. Sorry, I made amoeba a bit heavier, but okay. Even 10 to the 5 is fine. On the scales of the universe, it doesn't make a difference. Yeah. Thank you. So now the point is that everybody would tell you that something so big should be classical in a very good approximation. But actually what we are finding is that bigger things, bigger black holes and bigger cosmological spaces are more quantum, okay? And this is very surprising. In fact, black holes are ultra quantum. In a sense, they are the most quantum things that you can make. And I will explain in which sense, okay? And then we believe that this is the key for understanding all these so-called black hole mysteries. The black hole mysteries appear because normally we think that the semi-classical computations are applicable to real black holes. And I claim that they are not applicable, and that's the reason. Now, as you know, all these black hole mysteries are absence of hair, that black holes do not have memory about where they come from. Then there is exact thermality of Hawking radiation, Bekenstein entropy, and everything. Now, among these things, the Bekenstein entropy will be the only one that survives in the quantum picture. Everything else gets corrected. Of course, Hawking radiation is still there, but it will not be thermal, will be corrected. So the question is how strongly will be corrected. The absence of hair is gone, and so on. Now, yeah, so this is like pictorially a person, Alice, that is confused about black holes because she sees a thermal spectrum, and then she thinks that this must be a substance in thermal equilibrium, but okay, as we know, none of them work. You can get all possible crazy paradoxes if you make this assumption that semi-classical approximation works, because you get all Folk's theorems about violation of global quantum numbers by black holes and this kind of stuff, which you think is totally fantastic, right? That somehow a galactic-sized black hole should know whether your global quantum number should be violated or not, okay? Also information paradox and this kind of stuff. Now, these paradoxes are impossible to address in the semi-classical picture because they are a result of the semi-classical picture. So to address these paradoxes, you need a microscopic theory of a black hole. And I will try to provide such a theory. And then, as we will see, for example, black holes can carry perfectly nicely, consistently, for instance, baryonic hair, and could be even of astrophysical importance, and so on. Now, what is the key point? Now, we introduce black holes as a Schwarzschild solution, for example, in GR. In fact, you don't need even GR. Black holes were discovered even before. Okay, even in Newtonian gravity, you can understand that there must be black holes. Now, we introduce them through the metric. Metric is a classical field. It's an intrinsically classical entity because it's defined at every given point of the space-time. Now, on the other hand, if you are a quantum field theory person or even a quantum mechanical person, in quantum mechanics, there is a vacuum, which usually we define as a state with no particles, no occupation number, and then there are particles which are weakly coupled, and everything comes as certain state of those particles. In quantum field theory, there is nothing else, okay? Therefore, our key point would be that we should be able to understand curved backgrounds and black holes as states on Minkowski vacuum, but with certain occupation number of gravitons, okay? Everything you should be able to reformulate in this language, okay? This is the key point. Yeah, the off-shell, I mean, that's perfectly fine. I mean, look, we cannot debate an assumption. Let's make this assumption and see how far we go, okay? That's, I mean, I understand that this remark that you are saying, it's a fair remark. This is what comes first in mind, of course. We are taught in textbooks that the sources define longitudinal degrees of freedom. They are not real degrees of freedom, but things turns out that when you are dealing with space-times with horizons, things change because these things are essentially behave like Bose-Einstein condensates of gravitons at the quantum critical point, and then things are very different, okay? But yeah, this is an absolutely fair remark. Now, so basically, what is the key point? The key point is that if you have a gravitational background with characteristic curvature radius R, then you should think of it as a state with certain occupation number of gravitational quanta, okay, with characteristic wavelength given by this curvature radius, okay? This is the picture quantum mechanically. And then the radius will be given by, for black holes will be the gravitational radius, for the Hubble will be, for the cosmology will be Hubble radius, and so on, okay? Now the point is that now, once you make this assumption, there is no room to wiggle. You can give this assumption to in fact, to a first-year student, and anybody that knows about H bar omega can estimate how many quanta should be in this kind of configuration, okay, period. If you give the energy of the gravitational field and this assumption, you can compute it. And the number of quanta comes out to be very interesting because as if it depends on the surface, okay? You see that there is a dependence, R square over L Planck. L Planck is the Planck length. And so, but I didn't input any holography or anything like that. This is just simply counting number of quanta, period, okay? So now, the wavelength is given by R, and then from there you discover the following thing. Now, what are the gravitons? The gravitons are particles which have spin 0 and mass, spin 2 and mass 0, and they interact through certain rules given by Einstein, expansion of the Einstein curvature tensor, Einstein's Lagrangian. So I can define a quantum coupling between gravitons. That's obvious. We can define it. And the interesting thing about quantum coupling of gravitons, as you know, is that it depends on the de Broglie wavelength of the momentum transfer. So if you scatter two gravitons, the coupling depends on the wavelength. And this is the incredible property of gravity, that coupling changes from situation to situation. Now, once you realize this and then compare with the previous story, you realize that what you thought as a curved background with certain curvature radius is, oh, by the way, you can rewrite also alpha conveniently as a ratio of the Planck length square, because Planck length is defined through h bar times g Newton. Planck length square to the wavelength square, okay? As you see, alpha is an intrinsically quantum entity. When I take h bar to 0, it goes to 0 as it should, okay? L Planck also goes to 0 in that limit. Now, once you compare this with this, you discover that these gravitons with occupation number n, in fact, equal to 1 over alpha. Now, this is again very remarkable, because the number scales as area, although you never talked about area. This scales as area because the gravitational coupling has this property that it scales as area, period, okay? That's a property of gravity, that this quantum coupling scales as area in 3+1 dimensions. In any dimensions, by the way, would be exactly the same relation, okay? Now, this almost smells sort of holographic, right? You can imagine that there is something here that already related to the surface. Now, the point is, okay, now you can press on and say, oh, I have this situation. Now I should recover everything that I know in certain limit, okay? So, for example, you should recover how the curved metric emerges in this description. In this description, there is no curved metric. There is a Minkowski vacuum and occupation number of gravitons. Now, if I have a probe, this probe moves in this background and scatters. It's an intrinsically quantum scattering. Then, what notion of the curved metric emerges? This is a order by order summation of all the scattering diagrams, okay, in this background. And you can make one-to-one correspondence. Actually, it's totally straightforward. You can see, for instance, this corresponds to the leading term. So if everybody knows here that I can do, this is classical metric, G mu nu. I can expand classical metric in perturbations, in classical perturbations, okay? So the first order, second order. Now, I can obtain this expansion as a limit of a quantum process. But what is the limit? Limit is that when I take n to infinity and fix gravitational radius constant, okay? Now, there is one more parameter that you have to decide what to do, h bar. Now, on top of that, if you fix h bar non-zero, then this limit gives you semi-classical situation. In other words, you can have a quantum probe, phi, moving on a classical background. If you also take h bar to 0, then it will be simply classical situation. So this is how the metric emerges in this description. Now, these diagrams, they survive in classical limit. Of course, they survive in semi-classical limit, and they survive in classical limit. There is another set of diagrams which only survives in semi-classical limit. What are these diagrams? These diagrams are the following, that you have certain occupation number of gravitons, and of course it's an interacting theory, and in an interacting theory, as you know very well, you cannot keep system in the would-be ground state. It always will deplete. Why? Because particles interact, rescatter, and some of the particles will leave the condensate. Now, this is the diagram which reproduces for a black hole the Hawking's evaporation in the semi-classical limit. This survives in the semi-classical limit, but vanishes in the classical limit. In case of inflationary cosmology, this reproduces Starobinsky's gravitational waves or Gibbons-Hawking, depending whether you are in inflation or pure de Sitter. And so now, how inflation differs from pure de Sitter is that in inflationary space-time, you have occupation number of other quanta, inflatons. Now, if you have a system also has occupation number of other quanta, let me call them n phi, this number, then this depletion is